Welcome back, everyone. Today, we are diving into Chapter 7, Quadratic Equations and Their Applications. In this lesson, we will focus specifically on the first three core areas, Section 7.1, Solving Quadratic Equations, Section 7.2, Completing the Square, and Section 7.3, the Quadratic Formula and Applications. Let's get started on mastering these essential algebraic tools. Section 7.1. Quadratic equations have a degree of 2. This means they contain a squared variable, but no higher powers. Let's look at these three fresh examples. Notice that in each unique equation, the highest exponent of the variable is exactly 2. The general form of a quadratic equation is written as ax squared plus bx plus c equals 0, where a, b, and c are numbers and a is not 0. For instance, in our first example, a equals 1, b equals -5, and c equals 6. In our second example, a is 3, b is 15, and c is -42. One way to solve a quadratic equation is to factor it and then make use of the zero product property. This property states that if the product of two factors m and c equals 0, then either m equals 0, c equals 0, or both must be 0. Let's solve the quadratic equation x squared plus 3x minus 28 equals 0 by factoring. First, we factor the trinomial into x minus 4 multiplied by x plus 7 equals 0. By the zero product property, we set each individual factor to 0. Therefore, either x minus 4 equals 0 or x plus 7 equals 0. This beautifully gives us our final solution, x equals 4 or x equals -7. To solve a quadratic equation using factoring, we follow 3 steps. First, arrange all terms so that you have 0 on one side. Second, factor the non-zero expression completely if possible. Third, make use of the zero product property to find the final solutions. Let's apply these steps to an example. Solve x squared minus 2x minus 8 equals 0. The right-hand side is already 0, so we factor the expression on the left. This gives us x plus 2 multiplied by x minus 4 equals 0. By the zero product property, either x plus 2 equals 0 or x minus 4 equals 0. Therefore, our solution is x equals -2 or x equals 4. Next, let's explore the square root method. If you square a positive or negative number, you get the exact same answer. Therefore, if we take the square root of a number p, there are always 2 possible answers. In other words, if m squared equals p, then m must equal plus or minus the square root of p. Let's look at an example. Solve the quadratic equation x squared equals 49. To solve this, we can take the square root of both sides. By applying our property, we beautifully find that x is equal to plus or -7. We can also solve this exact same equation using the method of factoring. But remember, to use the factoring method, you must first arrange the terms into the form of something equals 0. Only then can you apply the zero product property. Let's solve the equation x squared equals 64 by factoring. First, we subtract 64 from both sides to get x squared minus 64 equals 0. Next, we factor this difference of squares into x plus 8 multiplied by x minus 8 equals 0. Using the 0 property, either x plus 8 equals 0 or x minus 8 equals 0. This beautifully results in x equals 8 or x equals negative 8, which means x equals plus or minus 8. Let's look at another application of the square root method. Sometimes, the left-hand side of a quadratic equation forms a perfect square trinomial. In this example, we want to solve 9x squared minus 12x plus 4 equals 16 by taking square roots of both sides. To solve this, we first recognize that 9x squared minus 12x plus 4 factors perfectly into the square of 3x minus 2. This gives us the equation 3x minus 2 squared equals 16. Taking the square root of both sides, we get 3x minus 2 equals plus or minus 4. Now we solve for x. This splits into two cases, leading beautifully to our final answers x equals 2 or x equals negative 2/3. Now let's move on to section 7.2, converting binomials to perfect squares. A binomial expression like x squared plus 6x is not a perfect square on its own. However, we can turn it into a perfect square trinomial by adding a specific constant. This constant term is always equal to the square of half of the coefficient of x. Let's look at an example. Convert x squared plus 6x to a perfect square trinomial. First, find the coefficient of x, which is 6. Next, take half of 6 to get 3 and square it. 3 squared gives us 9. Therefore, by adding 9, we beautifully create the perfect square trinomial x squared plus 6x plus 9, which can be factored as the square of x plus 3. Let's formalize the rule for completing the square for x squared plus bx. To convert any expression of the form x squared plus bx into a perfect square trinomial, we always add b over 2 squared. The resulting trinomial can then be written beautifully as the square of x plus b over 2. Let's look at example 2. Form a perfect square trinomial from x squared plus 10x. Here, our coefficient b is equal to 10. So, to complete the square, we add 10 over 2 squared. 10 divided by 2 is 5, and 5 squared is 25. This beautifully gives us x squared plus 10x plus 25, which simplifies perfectly into the square of x plus 5. What if the coefficient of x squared is not 1? With an expression of the form ax squared plus bx, we can still add a number to make it a perfect square. Let's look at this specific puzzle. If 2x squared minus 12x plus m is equal to 2 times the square of x plus d, what is m? To solve this, we first multiply out the right-hand side. Expanding 2 times x plus d squared gives us 2x squared plus 4dx plus 2d squared. Next, we equate the coefficients of x. This gives us negative 12 equals 4d, meaning d must be negative 3. Finally, we compare the constant terms. M equals 2d squared. Substituting negative 3 into d, we get m equals 2 times 9, which beautifully results in m equals 18. Now let's look at writing an expression of the form x squared plus bx plus c into the vertex form, x plus k squared plus m. To build our foundation, recall how we convert the binomial part, x squared plus bx, into a perfect square trinomial by adding the square of b over 2 to it. Let's try a foundational example. Convert x squared plus 12x to a perfect square trinomial. Here, our coefficient b is 12. So, to complete the square, we find half of 12, which is 6, and square it. 6 squared is 36. By adding 36, we beautifully form the perfect square trinomial x squared plus 12x plus 36, which is exactly equal to the square of x plus 6. More general quadratic expressions can also be written in this form. To do this, first take just the first two terms and add the square of half of b. Second, rewrite the binomial by subtracting that same added value to keep it balanced. Third, add the original constant c to complete the vertex form expression. Let's solve example 3. Express x squared plus 6x plus 2 in the form x plus k squared plus m. First, looking at the first two terms, b is 6, so we add 3 squared, which is 9. This gives us the perfect square part, x plus 3 squared. To balance the expression, we must subtract 4, then add our original constant c, which is 2. Combining -9 and plus 2 beautifully results in our final answer, x plus 3 squared minus 7. This is the most general case you can meet. Writing ax squared plus bx plus c in the form a times the square of x plus k plus m. First, factor out the coefficient from the first two terms. Second, complete the square inside the parentheses by adding and subtracting the square of half of the x coefficient. Third, distribute it back and combine the remaining constant terms. Let's look at example 5 with fresh numbers. Write 2x squared plus 8x plus 11 in the form a times x plus k squared plus m. First, factor out 2 from the first two terms to get 2 times open parenthesis x squared plus 4x close parenthesis plus 11. Second, add and subtract 4 inside the parenthesis since half of 4 squared is 4. This gives us 2 times the square of x plus 2 minus 8. Finally, combining -8 and plus 11 beautifully results in our final answer, 2 times the square of x plus 2 plus 3. Now let's apply our techniques to solve an actual quadratic equation by completing the square. First, take the constant term onto the right-hand side of the equation. Second, convert the left-hand side to a perfect square trinomial by adding the square of half the coefficient of x to both sides. Third, rewrite the left side as a perfect square and solve using the square root method. Let's solve example 1 with fresh numbers. Solve x squared minus 6x plus 5 equals 0. First, we move plus 5 to the right side to get x squared minus 6x equals -5. Next, half of -6 is -3, and squaring it gives 9. Add 9 to both sides. This simplifies to x squared minus 6x plus 9 equals 4. Factoring the left side, we get the square of x minus 3 equals 4. Taking the square root, x minus 3 equals plus or minus 2. This splits into two simple equations, beautifully leading to x equals 5 or x equals 1. Let's solve a more complex quadratic equation by completing the square. First, rearrange the equation so that all like terms are combined on the left-hand side. Then, if the coefficient of x squared is not 1, divide the entire equation through by that number to make it 1. To solve this, we first bring all terms to the left side, which gives us 2x squared plus 6x minus 40 equals 0. Next, divide the entire equation by 2 so that the x squared coefficient becomes 1, yielding x squared plus 3x minus 20 equals 0. Then, move the constant 20 to the right side and complete the square by adding 9 over 4 to both sides. This beautifully results in the square of x plus 3 over 2 equals 89 over 4. Taking square roots and isolating x, we find our final solution x equals negative 3 plus or minus the square root of 89, all over 2. Welcome to section 7.3. Today, we will discuss how quadratic equations can be in any variable. A lot of the equations you see may contain a variable other than x, such as y, z, or t. However, they are still quadratic equations and can be solved in the exact same way because the mathematical structure remains completely unchanged. Let's look at an example. Find the solutions of the following two quadratic equations. Equation A is x squared minus 5x plus 4 equals 0. Equation B is z squared minus 5z plus 4 equals 0. For equation A, it factors into x minus 4 times x minus 1 equals 0, giving x equals 4 or 1. For equation B, the variable is z rather than x, but it factors the exact same way into z minus 4 times z minus 1 equals 0, giving z equals 4 or 1. As you can see, both equations are really identical, only the letters have changed. The quadratic formula solves any quadratic equation in standard form. The solutions to the equation ax squared plus bx plus c equals 0 are given by x equals negative b plus or minus the square root of b squared minus 4ac, all over 2a. We can derive this powerful formula by applying the method of completing the square. Let's trace the algebraic derivation. We start with the equation ax squared plus bx plus c equals 0. First, move the constant c to the other side. Next, divide the entire equation by a so the leading coefficient is 1. To complete the square, we add the square of b over 2a to both sides. This gives us the square of x plus b over 2a equals b squared minus 4ac over 4a squared. Taking the square root of both sides brings in the plus or minus sign. Finally, isolating x gives us our completed formula. Let's practice a core application example using the quadratic formula. To solve the equation x squared minus 3x minus 10 equals 0, we first list out the exact values of a, b, and c. Here, a equals 1, b equals negative 3, and c equals negative 10. Now, we carefully substitute these three numbers into our formula. Substituting our values, x equals negative 3 plus or minus the square root of negative 3 squared minus 4 times 1 times negative 10, all divided by 2 times 1. Simplifying inside the root, we get 3 plus or minus the square root of 9 plus 40, which is 49. Since the square root of 49 is 7, this reduces beautifully to 3 plus or minus 7 over 2. Splitting into two cases, 3 plus 7 over 2 gives 5, and 3 minus 7 over 2 gives negative 2. Therefore, our answers are x equals 5 or x equals negative 2. Let's practice another advanced example using the quadratic formula. To solve the equation 2x squared minus 7x plus 4 equals 0, we first list out the exact values of a, b, and c. Here, a equals 2, b equals negative 7, and c equals 4. Now, we carefully substitute these three numbers into our formula. Substituting our values, x equals negative 7 plus or minus the square root of negative 7 squared minus 4 times 2 times 4, all divided by 2 times 2. Simplifying inside the root, we get 7 plus or minus the square root of 49 minus 32, which is 17. Since 17 is not a perfect square, the square root of 17 remains in our final expression. Therefore, our final answers are 7 plus the square root of 17 over 4, or 7 minus the square root of 17 over 4. Let's solve a word problem using the quadratic formula. The difference between a pair of numbers is 5, and their product is 150. If we call the lower number x, then the higher number must be x plus 5. Multiplying them gives the equation x times open parenthesis x plus 5 close parenthesis equals 150. Rearranging it to standard form gives x squared plus 5x minus 150 equals 0. Now, we identify a equals 1, b equals 5, and c equals negative 150. Substituting these into the quadratic formula, x equals negative 5 plus or minus the square root of 5 squared minus 4 times 1 times negative 150, all divided by 2. The inside of the root becomes 25 plus 600, which is 625. The square root of 625 is 25. This gives two cases for x, resulting in x equals 10 or x equals negative 15. Adding 5 to each to find the higher numbers, our final pairs are 10 and 15, and negative 15 and negative 10.